Okay, so back to this problem. Okay, so listen, I'm going to get real testy if I don't have everybody's undivided attention on this. This is because you don't get much time to go through this. All right, so given a zero, we want to find all the other real zeros of this polynomial. So what's it mean given a zero? Think what it means to be a zero of a function. To be a zero of a function means when I put that value in the function, I get back what value? Zero. When I plug in an x value of -3, I get back an answer of 0. And we could show that that works, okay? We want to come up with all of the other real zeros. So think about this now. If we know that the value of the function at -3 is 0, doesn't that mean it's an x-intercept, right? If I graph this function, and let's just pull up Desmos and graph it. Look, actually, I think I have a graph. Do I have a graph right there? No, I don't. I thought I did. Darn it, I don't. Okay, let's do that. So, if we graph this thing, so here's f of x equals x cubed plus 7x squared minus 33x minus 135. Okay, here's the graph, right? If I find the zeros, those are the places where if I'm plugging in those values of x, I'm getting back 0 for the function. Has to be that way, right? What's it mean to be an x-intercept? To be an x-intercept, it's just a point that's on the x-axis. The y-coordinate of every point on the x-axis is 0, right? So we know then that if -3 is an input value that gives us 0 as an output value, it's an x-intercept, right? Okay, so what? What does that help us with? Well, let's think about this in terms of writing the function in factored form. We always know that if I can factor a polynomial, then I can use the zero product property, right? So think about this. If I'm going to take, let's make this yellow. Okay, so if I take x cubed plus 7x squared minus 33x minus 135, and I want to find the solution, I want to find all the zeros, find out where that equals 0. Well, I want to try to hopefully break this thing up into factors, right? Right? Okay, well, what does one of the factors have to be? And let's kind of reverse engineer this. Right? We know that one of the zeros is -3, right? If we work backwards, normally we set each factor equal to 0 and solve. But now we're going to do the opposite. We're going to say we ended up with an answer of x equals -3, right? So what would I have to set equal to 0 to get that answer? Not 3. I would have to, if I want to get 0 on the right side, wouldn't I just add 3 to both sides?
Yes.
See what I'm saying? So I would get back the answer x plus 3 equals 0, right? You get this?
Yes.
Okay, so that's the answer. That must have been what we set equal to 0 to get the answer, right? So then that must have been the factor that we set equal to 0, was x plus 3, right? Okay, think about that. So -3 was the 0, x minus -3 or x plus 3 was the factor, okay? That always works, right? This gave us one of the factors, and we just want to find the other one, right? Okay, this is what we call the factor theorem, right? We know that, we already talked about the remainder theorem a while ago. We know that if I divide a function by x minus k, then whatever we get, the remainder is equal to the value of the function at k, right? And let's do just a little reminder of that. Like if we go back to, let's go back to this function right here. Okay, so if we evaluate this when x equals 3, what do we get? What is f of 3? What do we get? Is this what I want to do? No, never mind. I don't want to do that.
81 minus 16 plus 7.
Yeah, I don't want to do that. Never mind. I don't know why I was doing that. Let's go back to this guy for a second. Okay, so we know then that x plus 3 has to be a factor of this function, right? Okay, let's find out what this is then, right? This whole thing, the orange times the green has to equal the yellow, right? Agreed? Okay, so if I want to find out what the green is, and that's equal to the yellow, couldn't I just divide? I could set up an equation, right? I could set up the equation, the yellow polynomial equals x plus 3 times the green polynomial, and let's just call that, I don't know, let's call it q. And we'll just figure out what it is. We're going to solve for it. It's going to be some polynomial. What would I do to isolate q? I would divide by x plus 3, wouldn't I? Right? I would divide each side through by x plus 3, right? And what would I get if I did that? So those would cancel. We can do this synthetically, right? We can do this synthetically. So we end up with, what are the coefficients up here? 1, 7, negative 33, negative 135. What's the number that goes out front? That's supposed to be orange.
3.
No?
X plus 3.
Negative 3.
Negative 3, right? The 0 of the denominator, right, Willie? You should be looking up here, right? So negative 3, and there's the remainder box, right? Okay, so we go through the process then of dividing this out. So I bring the 1 down synthetically, right? 1 times negative 3 is what? Okay, plus 7.
4.
Negative 3 times 4.
Wait, repeat that.
Negative 12.
4 times negative 3.
Carlos was back there saying 12. Say it out loud.
Okay, Carlos, what is it?
Right, that's equal.
4 times negative 3. Carlos, I need you with me here. Okay. No, it's not 12, it's
Negative 12.
negative 12.
Come on, Carlos.
Okay, if I add those up, I get negative 45. So negative 3 times negative 45 is what?
Negative 3 what?
20 plus 15.
Positive
Negative
135.
135.
No, positive 135, right?
Yeah, it was negative 5.
So I end up getting a 0 remainder, okay? And this is what I'm left with then, right? I'm left with the polynomial. Doesn't that just mean x squared plus 4x minus 45? So that's what goes in here then, isn't it? Right? Okay, that's what goes in here. Whatever we got when we divided both sides by x plus 3. That's what we did synthetically. So we get x squared plus 4x minus 45, right? Okay, well then that's very helpful, right? Because now we already know that when I apply the zero product property, negative 3 is one of my zeros. I get that. I was given that information. But now all I've got to do is find the zeros of this one. See what I'm saying? So if we find the zeros of this one, I'm just going to set this, equal to 0 and solve, right? That's all we ever do is set the factor equal to 0. and solve. Well, how am I going to solve that quadratic equation?
Quadratic form.
I could certainly use the quadratic formula where A is 1, B is 4, C is negative 45. Are there magic numbers? Because that does make it easier. What would the magic numbers that multiply to negative 45 and add to positive 4?
9 and negative 5.
9 and negative 5, right? So I could say x plus 9 times x minus 5 equals 0. And so what do I get for that one then? What's my solution here? What's the 0 of that factor? Negative 9. And how about that one? Right? Okay, so it works, right? So now I'm able to get the other. I got one was negative 3. The other two are going to be negative 9 and positive 5, right? Okay, and why was I able to do that again? Why was I able to do this trick with the synthetic division? Now I remember why I had this other thing up here. So if we divide, let's say we want to evaluate f of x, make it easy, x squared minus 3x plus 5. Let's say we want to evaluate that at 2. Okay, what do I get if I plug 2 in?
4 minus 6 plus 5.
4 minus 6 is negative 2 plus 5 is what? 3. Okay? Well, what happens if I divide, I want to show you something here, just to remind you about something. What happens if I divide the polynomial x squared minus 3x plus 5 by x minus 2? I mean, by x minus 2, which means I'm just plugging a 2 out there, right? Because what does this really represent? It just represents if I divide this polynomial, x squared minus 3x plus 5 divided by x minus 2, right?
Should it be minus 2 or plus 2?
It'd be minus 2, because remember the 0 of the denominator is 2, right? So the fact that that's x minus 2 makes that a 2, right? Okay, well, what do I get if I do this process? I bring the 1 down. 2 times 1 is 2. 2 plus negative 3 is,
Negative 1.
okay, negative 1 times 2
Negative 3. Negative 2.
is negative 2, and if I add those up, what do I get?
Negative 3.
3. Is that an accident? No, it's not, right? That's what we learned the other day. That's the remainder theorem, right? Plugging, if I'm dividing by x minus k, if I divide some polynomial by x minus k, like I did here, right? If I divide this polynomial by x minus 2, whatever I get for the remainder is always going to be equal to what I get when I plug, in this case, whatever I'm subtracting from x into the polynomial every time, right? That's always true. So that's the assignment 6.6 deals with that. It's no big deal, right? If I divide by x minus k, the remainder is always equal to what I get when I plug k, whatever that number is, into the function every time. Okay. Well, we took advantage of the fact that then that means, right, that means that if the remainder is 0, yeah. Where's Noah? Pass it back to Noah. So so what's that mean here then? This is just another way of thinking about what we got from our graph. If I plug negative 3 into the function and get 0, then doesn't that tell us that x minus negative 3 is a factor? Right? Because whatever the number that we're plugging in, if I subtract that from x, that's got to be a factor of the polynomial. What's x minus negative 3? X plus 3, right? And so that's a factor. Agreed? Okay? So if we just synthetically divide this by x minus negative 3, by x plus 3, whatever we're left with is going to give us the other polynomial whose zeros I need. Let's try one more of these.